Okay, so this far we have been working with exponential functions and equations. So let me just show you what you have for the exponential equation. Okay, and this is where we've said basically y is equal to a to the x. So this is your exponential equation slash function. We've also made the restrictions here that your base must be positive and your base cannot equal 1. We showed how with the graph it passes the horizontal line test, which means it's going to have an inverse. So a quick sketch of the graph to remind you of what we had going on. This is your exponential. Something along those lines. So it passes the horizontal line test. It has an inverse. And what we want to look at today is what does that inverse look like? Okay. So the inverse is what we call the logarithm. So we're going to be looking at logarithmic equations and functions. Now, if you remember what we said about inverses, the key thing is that when you go from a function to its inverse, you swap out the x for y and the y for x, right? That's the big thing about inverses. So if I take this setup here for the exponential, that means for the logarithmic equation, it's going to look like instead of y, we're going to write x equals, the base is still there, and instead of x, we write y. But we typically like to see this from the perspective of y, and so we have created the function y equals log base a of x. Okay. Please understand that this is not a to the x down here. This is log, and I'm telling you what the base is. In much the same way you would indicate an index in that little nook on a radical, we're going to indicate my base as a little subscript next to the word log. You can never write just the word log because that means nothing. That would be like you writing the square root symbol and having there be nothing inside of it. It's dumb. You don't do that, right? The logarithm is a function, the log of something. There always has to be an input value here, all right? Now, let me show you how things are all connected with logarithms. That way you don't get confused. You might have had confusion in high school. We're not going to have that now. If I were to write 2 to the third power, you guys know what that equals, right? 8. Good, good. One person out of the whole class. You hear that? Only one person. So 2 to the third is 8. The rest of them are still waking up. 2 to the third is 8. This is a known relationship, right? Now, I want to look at this relationship from different perspectives. For example, let's go back to something we've already seen, and let me write this. If I write the cube root of 8, what's the answer? You know the answer is 2. And the way that we know that the answer is 2 is because of the little number games that we play. The number game that we would play for this is in our little thought bubble. I would ask you to figure out what to the third power, see the index tells you the power, right? What to the third power is equal to 8. And so you play whatever that game is until you come up with the correct answer. And the correct answer is 2, right? That's how radicals work. With radicals, you know the power and you know the end result. You're trying to figure out what was raised to that power. Again, it's still connected to this expression up here. Logarithms still work with the same relationship, but they ask for a different piece of the puzzle. You're going to see something that says this: log base 2 of 8 equals a number. And here is the hidden question in this expression. The hidden question is, this is my base 2. 2 raised to some power is supposed to equal this input value of 8. So with logarithms, you're not trying to find the base like you're trying to find with radicals. With logarithms, you're answer relates to the power. So how would you answer this question? What power of 2 gives you 8?
3.
You would say 3. And that's the answer that we say right here. In all of these different expressions, we are still working with 2 to the third equals 8. With a radical, I'm trying to find the base. With a logarithm, I'm trying to find the power. That's it. Does that make sense? So the answer to the log is the power. The answer to the log is the power. I would ask you to repeat that with me, but since I'm recording, you might be a little camera shy. The answer to the log
is the power.
Is the power, yes, with such enthusiasm, right?
Say it again.
No, that's all right. I'm good. Yeah, I got all I wanted out of you. So if I ask you this, if I say, what is log base 7 of 49? You have to make sure that you are playing the right number game.
7 to the what equals 40.
Right, and you can even write it like this if you want to. You could write 7 to the question mark, or you could even say 7 to the x, like you're trying to solve an equation. 7 to something equals 49. So this is your thought bubble. And 7 to the what power is 49?
Squared.
7 squared, so the answer is 2. The answer to the log is what? The power. You dig? Cool, cool. If I say, what's log base 5 of 125? As we saw on the previous page, we know that 5 to the third is 125. Okay? So again, this is coming from the fact that 5 raised to the third power is 125, and as we already said, the answer to the log is the power. What if I switch this up a little bit and I say log base 5 of 1 over 125?
1/3 is.
It's a negative.
Oh, negative.
Now see, this is where you have to figure out, is my answer supposed to be a negative or a fraction? What power would get you to 125? 3. But to make it the reciprocal of that would be the negative third power. Is that good?
So it's the reciprocal. I'm just missing why the negative indicates a fraction. It's probably simple.
Well, it goes back to this. So 5, if you raise it to a negative power, you would have to address the issue of the negative by making it a fraction like this, 1 over 5 to the third, before it becomes 1 over 125. Okay? So it's properties of exponents that we just can't get away from. Now, let me do you even one better. If I do log base 5 of the 7th root of 25. If I didn't have the root there, if I didn't have the radical and I just had log base 5 of 25, the answer should be 2, right? What causes me to have a radical? What's the connection with the power and the radical?
The inverse of the radical would be to bring it to the 7.
That's not what we're saying. We're not talking about the inverse of the radical.
You're getting rid of it, right?
No, we're not getting rid of it. We're trying to figure out this. And this is where off to the side you can figure this out. So this is like asking 5 to the what power is equal to the 7th root of 25. This is what we're trying to ask. You guys with me on that? Now, if you think back to the example that we did at the beginning of class today, we were able to rewrite this and say 5 to the x is equal to the 7th root of 5 squared, right? I apologize for running out of room here. So we get 5 to the x equals, this is still 5 squared, right? Where does the index go in terms of my power?
Oh, you make it into a fraction, huh?
We make it into a fraction to be to the 2 over 7th power. Please make sure you understand this is 5 to the 2/7, not the mixed number 5 and 2 over 7. And so now this kind of goes back to solving those exponential equations from the past few days. Since these guys have the same base, what can you say about the powers?
X equals 2, 7. They're the same.
You can say that the powers must be the same. So x equals 2 over 7.
Makes your answer 2, 7.
And so that means my whole answer is 2 over 7, like that. Isn't that totes fun?
It is fun. It's challenging.
Well, I think that the way to make these problems less challenging is to make sure that you know your powers. Because as long as you know your powers, you knock this stuff up very, very quickly. But if you're sitting there struggling, like, oh, I can't remember what power of 5 gives me 125, or if it even does have a common base, that's where you get thrown off. Because I could then give you a question like this. And in a little bit here, we're going to show you some easier ways of tackling these problems. If I say log base 8 of 32, the students who fall asleep in class or are on their cell phones are going to miss this one. And they're going to say the answer is 8. Because for some reason they have it in their head that, oh, if I've got an 8 and 32, the answer's got to be 4. But that's not what this problem is asking. This problem is asking what?
8 to the what equals 32.
And so if I write that underneath here, maybe in a different color so I understand this is kind of like my scratch work, my thought work over here, 8 to the something equals 32. So if I look at this in terms of an exponential equation, I'm going to be okay. Because as it stands right now, there's not a nice power of 8 that gives you 32. Because if you think about it, 8 to the first is 8. 8 squared is 64. That's too much, right? Well, what that does tell us, though, is that the answer should be where?
Right in the middle.
Between 1 and 2. That does not mean 1.5.
Right.
But it's got to be a value between 1 and 2. So when I get to the end, the answer has to make sense. So let's keep going here. What's the common base for 8 and 32? 2. So I can rewrite 8 to be 2 to the third power raised to the x. 32 is 2 to the fifth power. All right, so power to power means I'm multiplying. 2 raised to the 3x equals 2 to the fifth power. Since these guys have the same base,
3x equals 5.
3x equals 5, so x equals what?
5/3.
5/3. Isn't that a number between 1 and 2? If you make that a mixed number, that's 1 and 2/3, so yes, that's between 1 and 2. So I come back up here and I say definitively that this is equal to 5 over 3. So we can make that conversion back to an exponential equation, back to a realm where we are very comfortable, and we solve it.
So like